One of the biggest challenges in a Calculus 2 course or Calculus BC course is deciding if a series converges or diverges and really deciding which convergence test will be the best one to use. So I want to go through my thought process on picking the right test or picking the most efficient test. So I'm just going to shorthand. I'm not going to continuously write, n equals 0 or 1 or whatever. And infinity, this is just going to be my shorthand. And then this box, this is whatever expression or whatever, function kind of looking thing is inside it. All right, so let's go through the tests as kind of like a flow chart of what I would use. The first one I'd use is called the nth term test, or sometimes called the divergence test. And this is where you just say, is the limit of my expression equal to 0? And if the answer is no, then we're done. It diverges. If the answer is yes, well, then we have to go to a different test. So let me give you an example of something that would be no. Let's say that my original series was n over 2n plus 1. Well, if you took the limit of this expression, right, you just looked at this and said, what is the limit of that? Well, the limit of that expression is 1/2. It's not 0. So the minute it's not 0, you know that this thing diverges. You don't even have to continue. Now, if the answer is yes, we go to a different test. The next one I look for is the geometric test. And a geometric test concerns things that almost look like exponential functions. They've got some number raised to the nth power. And you look at that number, that's all you need to look at, and you say if that number, whatever it is, a, is between -1 and 1, it converges, otherwise it diverges. So a quick example, if I had 2/3 to the nth power, that would converge. But if I flipped it and I had 3/2 to the nth power, that would diverge. So that number being raised to the nth simply needs to be between -1 and 1. Now, if it doesn't look like that, if it isn't in that form, we go to our next test. Our next test is what's called a p-series test, and it's in this form. It's some number on top. I wrote 1. It doesn't have to be 1. It could be any constant. And it's got n to a power. So some number over n to a power. And it converges as long as that power is greater than 1. We get convergence. So let's look at one. If we had something, again, there's nothing important about that numerator being 1. So I'm going to write 3 over n squared. Well, the power is bigger than 1, so this converges. On the other hand, if it were 4 over n to the 1/2, well, that would diverge because that power isn't big enough. So that's the next thing I look at in this thing. Now, if it doesn't look like that, then we go to the next test, which would be the root test. Now, the root test looks kind of as a setup, very similar to a geometric, but instead of a number raised to the nth, it's an expression raised to the nth. But we almost treat it like a geometric, and we evaluate the limit of what's inside here. So I'm going to put just the limit as shorthand. And we say, well, what is the limit of what's inside there? And then we basically use the same geometric rules. So let me write an example here. Let's say we had 2n plus 7 over 3n plus 1 all to the nth. So that's not a number to the nth, it's an expression. But if we said, well, what is this expression doing as n goes to infinity, you'd say, well, it's approaching 2/3. And if we go back to our geometric rule, 2/3 is between -1 and 1, so that would lead to convergence. Whereas if it were something like 5n plus 7 over 3n plus 2, you'd say, well, the expression inside here, this limit is 5/3, and using our geometric rule, because that isn't between -1 and 1, that would diverge. So that's the next one I would go to. If it doesn't look like that, then we go to another test. Now the next thing I would use, the limit comparison test is best for when you have kind of complicated looking series, but they have the same function types in the numerator and denominator. So let me write an example here. Let's say we had something like this. Something like that. So even though they're complicated, they don't look as simple as a p-series or anything, it's at least the same types of functions. They're both power functions. They're both n to powers. And what you do is you look to the most powerful piece on both the numerator and the denominator. And I'm solely basing that on the fact that they're the highest powered things. And I make a reduced fraction out of them. So my reduced fraction, 2n cubed over 6n to the 5th, would be 1 over 3n squared. So just reducing that. And then I use my other rules. This is a p-series. In a p-series, the power just needs to be bigger than 1. This converges. And therefore, so does this. Let's do another one like that. Let's look at something like this. And now I would say, well, the most powerful part on the top, most powerful part on the bottom, 7 to the n over 4 to the n. I make a reduced fraction out of that, and I would get 7 over 4 all to the n. That's geometric. It's bigger than 1, so it diverges. So the limit comparison is really when the most powerful types of things on the top and bottom can be worked with and simplified. You can isolate, this is the best, this is the most powerful part in the numerator, this is the most powerful part in the denominator. They're similar to one another, and I can algebraically manipulate them and make a simpler comparison. That's why it's called comparison. There is more to the proof, by the way, for this one, but I'm just trying to show you the kind of quick and easy way to use it. But there certainly is a little bit more to this one. Now, if it doesn't look like that, then we go to our next test, called the ratio test. And the ratio test is used for when those kind of algebraic manipulations can't happen, but also it's used a ton with mixes of functions, and especially exponents and factorials. So ratio test, an example of something that I'd use ratio test for, let's say it was something like this, where it had an exponential, kind of a geometric looking numerator, and then a factorial denominator. And the ratio test says you take the n plus first term, so just putting an n plus 1 in every time I had an n, divide it by the nth term, and take the limit. And you should be showing that this is, if you're going to get convergence, this limit should be less than 1, because you're showing that when I take a term and divide it by the one in front of it, I'm consistently getting a smaller than 1 ratio. When we divide by fractions, we of course multiply by the reciprocal. We can do some reducing here. If you want to see more of this, I have another video, or many videos, just on ratio tests, but I just wanted to kind of talk about where I would use them. So this converges because that ratio comes out less than 1. So again, this is when you see exponentials, when you see factorials kind of mixed, use ratio test. Okay. Now, if these 6 don't work, and these are definitely the ones I would like to use, then we go to the final 2 that I think of, which are integral test. And this is for times when you can't really see any of the other ones working, but you think I could write an improper integral that has the same kind of expression inside it, and I can evaluate that improper integral. And, see if that converges or diverges. And the final one is what's called direct comparison. And direct comparison is, it could also, work for things like natural log. That's a good time to use it. Let's say you had something like this. 1 over n is a divergent series. And if you take the natural log of something, you make it smaller. If you make the denominator smaller, you make the fraction bigger. So this is greater than. And if something is bigger than a divergent series, it also diverges. This is direct comparison. You compare it to a known series. Again, this is, this one is one I kind of try to avoid at all costs. Now, the last thing to look for is the series alternating? And an alternating series often has a -1 to the n or n plus first out front of your expression. And this is a two-part test. The first part is just evaluating the limit inside that expression. And if the limit is equal to 0, you get convergence. That's all you need. And if that's true and this expression converges on its own, then that's called absolute convergence. So, for example, if I had something like -1 to the n and 1 over n squared, just covering this up for a second, 1 over n squared going to infinity has a limit of 0, and 1 over n squared is a convergent p-series. So basically, you just ignore that it was alternating and say, is the limit 0? Yep, it converges. Does the series converge even without this? Yes, then it's absolutely. So we say converge absolutely. If it was something like -1 to the n and 1 over n, then you'd say, well, 1 over n has a limit of 0, but 1 over n is a divergent series, so this converges, but only what we call conditionally, because the condition being that it was alternating. So those are the order that I would kind of run through these. So nth term, just is the limit 0? No? You're done. It diverges. If the answer is yes, we go to geometric. Geometric is something that looks like that, a number to the nth power. If it's not, we go to p-series. P-series is one where it is a number over n to a power. Okay. If no, that's not it, then we go to root test. Root test is a function to the nth. Looks very similar to geometric, very similar rules. If no, we go to limit comparison. Limit comparison is one of my favorites, very powerful. Okay, and that's for things that look like similar function types. If that doesn't work, we go to ratio. I'm just going to make a note. Ratio, you should look for factorials and function mixes. Okay. Those are the big ones you want to work. If those don't work, look for integral or direct comparison. And these ones, when I see a natural log function, I'm often looking to use a direct comparison or integral test. If this video helped, please like and subscribe for more math.